speaker is the next faculty speaker is Dr. Trevor Carlson. Trevor is an assistant professor at the School of Computing. He obtained his PhD from Ghent University in Belgium and a master's and bachelor's degree from Carnegie Mellon. He has actually a lot of industry experience. He has worked as a computer architect at IBM, Intel, and IMEC. His research very much focuses on secure and efficient computing and accelerated design, which is also related to the topic of his talk today, which is security in computer architecture research, protecting processes with low overhead methodologies. Thank you very much, and over to you.
Thanks so much. Can you hear me okay? Yeah, great. And I guess you can see my slides. So thanks for the introduction. That's great. And we're going to talk a little bit about what computer architecture is and, building of systems and what that looks like today. Actually, the previous speaker talked a little bit about drones and how he was using those to do the analysis that he really wanted to do on the different islands and atolls. And if you think about it, when we're building those drones, we need to use, really high efficiency systems. If you want to add, if you want to do, island identification, and you want to fly your drones around and find out what's out there, then you really need to make sure that your computing system is quite efficient, or else that will drain your battery quite quickly. So these are some examples of the kinds of things that we're doing in our group. We're building these high efficiency edge devices. Today we're going to talk a little bit in detail about efficient server systems. We also do something called simulation modeling and sampled simulation. And I can go into more detail on these things if there are questions. But the idea there is, how do you predict tomorrow's computer, the performance of tomorrow's computer, using the computers of today? We don't have them yet, but we want to be able to figure out what to build in the future. Security is going to be the primary target that we're going to be talking about today, but I'm just giving an overview of kind of things that we do in our group. And we also want to build accelerators that maybe are able to speed up computation. So up to this point today, we've been doing a lot of things with our general purpose CPUs. So the CPU in my laptop here, or the CPU in my mobile phone. But what's happening more and more is that people want to accomplish more with less. And the traditional CPUs have shown some limitations with respect to how fast they can go and how efficient they can be. So what people are doing now are building specialized devices, specialized hardware that can provide speed ups and energy efficiency numbers from 10, 100, or even 1,000x over what your traditional CPU is doing. And that's the kind of thing that we're trying to look at here. Let's see here. So one thing I want to talk about, as a researcher is, from my perspective, what is innovation and what is research? And people have different definitions of this. But my view is, when I started working, as Jessica mentioned, I started as an engineer working in industry, and we are looking to solve complex problems quickly. And when we were in industry, sometimes we need to apply some brand new ideas, and we need to apply those ideas to what we're doing in engineering. And so maybe we need to, in my definition, use something called innovation, which is using new research to target the engineering problems that we have. But here at the university and as a PhD student, one of the goals is to really solve problems in brand new ways that no one's really thought about before. And that's really what we're trying to do here. We're trying to figure out, how can we make our processors faster, make them more secure? And one of the big challenges is, how can you make a processor secure and efficient and fast? And right now, that's a really difficult problem. Many people have been trying to protect their systems from attacks and from hackers And it's possible to do, but I think people are not willing to give up their high performance machines. So usually the slowdowns are just unbearable. So what we're trying to do is figure out how can we do things in new and different ways, such that we can get both the performance and efficiency, as well as the security that we need. And in fact, one could argue that a little bit of research really is doing engineering, doing innovation. And what that means is looking at other researchers' work, understanding what they do, and then implementing it locally, and then trying to understand, like, what did they do? What are the limitations of their work? Can we try to solve that problem in a different way, in a better way? And that's what we try to do in this group, and actually in all research groups here at NUS. Once you get to the research part, right, with respect to solving problems in new ways, and that's how we work, and we publish papers, and we move on from there. So basically, what is research for me? And research for me is, building state-of-the-art, applying it to new problems, and then determining where those solutions are unable to solve the new problem. So for example, maybe there's this new security defense, but it makes your CPU two times slower. Who wants a phone that's 2 times slower? Anyone? Probably not. So we need to figure that out, right? How do you protect your phone while still making it fast? And then once we find those solutions, then we want to convince others that this is an important solution, and that this is a novel solution, and that's what we work on as researchers. Okay, so that's just a little bit of overview of what I think research is, and what we do in our group with respect to forming research ideas. And part of the other thing that we do in our group, we do a lot of thinking about what the future is going to hold. And so one of the things is we want to build, like, wouldn't it be great if our computers or our systems were autonomous? They could communicate with each other. They could be distributed in low power and highly efficient. So you sort of see, like, the beehive as an example of this highly parallel, highly efficient system that's been honed to work really, really well. So really, and what we're trying to do here is to build something like a beehive, where the bees are our CPUs or our accelerators, and maybe the hive itself is a silicon substrate. When you look at the types of platforms that computing is in, right, we see compute in sensors and cameras and mobile phones, but you also see things like, maybe you put a 5G base station in your lamppost. Maybe in other items around the city, you'll put things, you'll deploy IoT sensors and devices. And of course, data centers are extremely popular, and we see those here in Singapore quite a lot. And this is one of the goals that we have, really. Can we build more capable systems that are still fast? Can we build processors that can maybe not be as hot or not use as much energy, and therefore, reduce electric bills? There's been an interesting, there have been some interesting developments where people have hoped that their new designs of their processors would lead to more sustainable solutions. But what's happened, in fact, is that people continue to use the machines up to the limits of their power. So, for example, maybe your machines are 20% more efficient. Well, instead of using 20% fewer machines, well, they'll just buy 20% more machines, and they'll do more work. So this is an interesting phenomenon that we need to think about as computer architects and as computer scientists. How do we solve this problem of efficiency? So this is something to think about. And this was an example of a project that we did not do, but a project that was over from ECE, where they built this really cool IoT device. And now you can think about, how do we combine technology so that we can, in this case, it was a, it was a swan here. It looked, it's trying to see if there's any pollutants in the water. And, what it's not, it's sort of meant to blend in, right? Technology blending in instead of technology being so obvious, or at least maybe in the way. So this was, I thought, an interesting idea, and the kinds of things that you want to do when you build highly efficient systems. So now I'm going to switch gears a little bit and start getting a little bit more technical. And some of these things might be extremely technical, but I think that's okay. I think the point is that if there are things you might not understand, we can either talk about them now. If there's questions later, let me know. But I want to give people in the call today a little bit of a feeling of what kind of stuff we're doing. And to do that, I thought going a little bit more technical would help. So in general, all devices today, be your phone or tablet, desktop machine, or even your server system, is power limited. So what that means is it can only run so hot before maybe the chip melts, or the chip melts the casing of your mobile phone. And we don't want that. So what we want to do is we want to make sure that we don't exceed the power limits of our systems, but we want to do more and more and more. And there's this technique in computer architecture, or at least in VLSI design, silicon design, called Dennard scaling, which allowed us to do more and more. And people usually refer to this as silicon scaling. And because of technology limits, some fundamental limits behind the transistors, actually it's coming to an end now. And so what that means is we can no longer keep utilizing more and more transistors all at the same time. And then what about cost, right? Things have been getting cheaper and cheaper, and Moore's law sort of has helped us to put more transistors per chip. But in fact, this is also reaching its end. So what does this mean for people like me, computer architects, and the researchers in the area? Well, what this means is that we need to figure out interesting techniques that can allow us to both perform or have high performance systems that are doing more with less. So that's really the challenge. And we've looked at different applications and methodologies to understand the applications. We've built simulators in the past, and we've used something called analytical modeling to understand those systems. And we've also done something called sampling, which allows us to build systems and then understand the future workloads without actually having to simulate the whole thing. One of the problems with simulators is that they're 10,000 times slower than your real machine. So instead of one day, it might take years. But with these sampling techniques, we can significantly reduce the amount of work we need to do. Other things that we've been looking into in our research here, we've been developing new processors. I'm not going to go into all these details, but the point is that we've been developing high efficiency processors, high performance processors. And by doing that, we've been able to basically do more with less. And the goal of our group is to continue in that process. In addition, we've been working on security solutions. And on the upper left here, we have a new security solution with something called a trusted execution environment. So some people might know this as SGX, similar to SGX. In the middle is a new attack that actually can extract data from your CPU. And so we present this new attack, but we also present the defense against it. And then in the upper right is a new defense methodology to protect against EM attacks. But what I want to talk about today is an upcoming paper that we're going to be presenting in just a few weeks over in San Diego at ICCAD. And this is fast, robust, and accurate detection of cache-based Spectre side channel attacks. So I want to talk a little bit, I'm not going to go into all the details here, but what I'd like to talk about a little bit is what's going on with side channel attacks. So people might have heard in the audience, you might have heard about Spectre and Meltdown, these big flaws that have been found in processors. And what's happening is we see more and more that there are quite a few exploits where you can look at a CPU and maybe extract your private key and maybe decrypt private information, extract private information without you knowing, and that's quite bad. So this affects all modern systems, and in this case, there's a few steps in how to do this. What you need to do is you actually use something called speculative execution. So speculative execution is a process by which a processor in your CPU takes a guess into how the user's application will run. And sometimes with this speculative execution attack, it will go the wrong way, affect how the system behaves, and then it will recover and start to execute in the proper direction. Well, it turns out that when it goes down this wrong path, your attacker can trick the CPU into releasing or leaking some data. And that could potentially be your private key or some other critical information that you don't want others to have. So all of a sudden now, you're executing your normal program, and an attacker comes around and is able to start extracting information from your system. So a side channel is a way for attackers to come and try to extract this data. And I'm not going to talk about these details, but the idea is that as a computer architect, we have to go in and understand all of the details of the system and how the attacker can go in, how it can trick your hardware into releasing the secrets. And what this work that we're talking about is going to talk about in the coming months, what we're going to at the end of this month, is yes, people can attack traditional CPUs. And it turns out that there are lots of these mitigations, like I mentioned earlier, that make the attacks, that make your CPU 2 times slower, 3 times slower. Now, what we want to do is, with this work, we want to show that maybe we don't need to keep those defenses on all the time. Maybe we can wait and watch for an attacker. And if the attacker does come and try to extract your secret key, well, then you block things and you say, okay, we will not let you extract the information. And that's really what the goal is of this work, is to be able to quickly monitor and extract the information. What's also interesting is that there have been many solutions in the past that use machine learning to detect problems. And machine learning actually had done a really, really good job at finding when an attacker is trying to extract your private information. But it turns out, and again, I won't go into these details, but it turns out that when you craft some very specific attacks, you can actually trick the AI and fool it so that it won't detect your attack. And so part of this work, the first part of this work, really shows that it is quite straightforward to trick the AI. And we have some other examples here. I'm not going to go into the details again, but we can see the accuracy at the bottom here drops from a 99% down to 12%. So now all of a sudden you think you're secure, an attacker comes in and is able to fool those traditional AI work implementations. So what we found is they're quite fragile. And instead of using these AI techniques, we want a robust, a fast, accurate, and efficient solution. Like I mentioned before, this fast and accurate is extremely important for us as architects. And so instead, we did not look at AI, but we looked at understanding all of the pieces fundamentally and sort of monitoring the system as a whole. And we built some state machines that allow us to say, is there data being leaked? Has that happened? Oh, if that happens, then we notify the hardware, notify the system. these are the kinds of things that we implement here. When we, as architects, we look at the processor and we add different components in order to do this, in order to track things. So we have additional components here to track the system and to make sure that nothing is leaking. And if there is a leak, you can see here that we raise an alert. I'll skip past some of this detail, which is basically talking about how previous works are extremely, can be fooled pretty easily. But if you look at our work here on the right, you can see that the accuracy remains high. And I'll skip this in the interest of time. Overhead. So what happens is there's always a trade-off with these security designs. So we are quite accurate now, but the overhead is for power overhead is less than 1%, which was the limiting factor that we were talking about before. So if it's only a 0.5% or a 1% overhead, then that's not bad at all. Right. So basically what we've done with this work, and this is just one example of some of the work that we've been doing, but what we've done is we've shown that some initial security work that looks to improve efficiency can be fooled. And once we realized that as part of our research, we said, okay, how can we improve these detectors so that to prevent this from happening in the future? Yeah, and with that, I'll take any questions there might be.